Hey, what's up, Mr. Sada here. Today we're going to be talking about the electromagnetic spectrum. Hopefully by the end of this video, you'll be able to tell somebody what the electromagnetic spectrum is and what the different waves are that are on the electromagnetic spectrum. All right, let's get started. Before we can talk about the electromagnetic spectrum, we have to talk about light as a wave. All right, so one way to think about light is that it travels as a wave. A wave is just a disturbance in some medium. So for example, water, air, space, we can see in the picture on the right side here, we have a wave which is moving through water. A wave travels through a medium, but it doesn't transport material. A wave transports energy, but doesn't transport matter. So the wave is not moving water, the wave is moving energy. A wave can also carry information along with it. So for example, dolphins send ultrasound waves, and they use those reflected waves to detect obstacles and prey. So not only can a wave transfer energy, but can also transfer information. Right, so here's our electromagnetic spectrum. All of these different pieces that are on here, for example, radios and cell phones and microwaves, these are all different types of waves that are on the electromagnetic spectrum. So we have radio waves and cell phone waves, microwaves, radar waves, infrared waves, and so on. And all of these different waves operate at different frequencies. If you remember, frequency is the amount of waves that pass in a given amount of time, right? So we can see some of them have really low frequencies, and other waves have really high frequencies. And we'll talk more about that in a little bit. Right, so what is the electromagnetic spectrum? The electromagnetic spectrum is the complete spectrum of light, including radio waves, infrared waves, visible light, ultraviolet light, X-rays, and gamma rays. So there's a lot of different parts of the electromagnetic spectrum that we can't see. We can only see visible light, but there's lots of other parts to the electromagnetic spectrum. Now, an electromagnetic wave consists of electric and magnetic fields which vibrate, thus making waves, and that's where we get the word electromagnetic from, because we're combining electric and magnetic fields, so we get an electromagnetic wave. And electromagnetic waves are transferred by radiation. If you remember radiation from when we talked about heat transfer, radiation is the same heat transfer property that's used when, for example, you're holding your hands over a heater, right? And you're feeling the warmth coming off the heater. That's radiation. This is transferred in the same way using the same process of radiation. Right, let's look at wavelength, frequency, and energy. Now, learning about wavelength, frequency, and energy will help us to understand a little bit more about how these different waves are plotted onto the electromagnetic spectrum and how these different types of waves are different. Right, so since all light travels at the same speed, travels at the speed of light, the wavelength and frequency have an indirect relationship. Indirect means as one thing goes up, the other thing goes down. So light with a short wavelength will have a high frequency, and light with a long wavelength will have a low frequency. Light with short wavelength have high energy, and light with long wavelengths have low energy. Right. So if we look at the picture on the right, when we have a short wavelength, you can see my waves are really, really short. They're all squeezed together. We have a really high frequency. There's a lot of waves passing in this amount of time. To contrast, when we have a long wavelength, my waves are much more spread out. We have a lower frequency. There's less waves in a given amount of time, right? And our speed for our wave, the speed of light, is equal to the wavelength of the wave times the frequency of the wave. Right, the electromagnetic spectrum again. So human eyes are only able to process information from the visible part of the spectrum. Toward longer wavelengths, the spectrum includes infrared light, microwaves, and radio waves. Toward shorter wavelengths, the spectrum includes ultraviolet light, X-rays, and gamma rays. So there's a lot of different parts of the spectrum that we can't see. Right, and all of these are forms of electromagnetic radiation. Any of these different types of waves on our spectrum here are all electromagnetic waves. Right, so let's look at radio waves. Right, so radio waves are low energy waves with really long wavelengths. They include FM, AM, radar, and TV waves. They're very low frequency, and they're used in many devices such as remote control items, cell phones, and wireless devices. Next, we have microwaves. Microwaves are longer than radio waves, but they're shorter in light. They're shorter than light and infrared waves. So microwaves were first used in radar, but now they're used in communication, medicine, and they have a consumer use as well. For example, microwave ovens. So you're probably familiar with microwaves as the thing that heats up your Hot Pockets, and it is the same type of wave, but all of the wavelengths of microwaves are not the same, so there's a range. So for example, we can use cell phones or walkie-talkies that operate using microwaves, and there are microwave ovens that also operate using microwaves to cook food. Right, next we have infrared waves. Infrared waves are invisible electromagnetic waves that are detected as heat. Right? They can be detected with special devices such as night goggles. So here on the picture on the right, that's a picture using a night vision filter on a camera. You can see that part of this woman's back is red while her hair is lighter in color. Now, that red color tells me that more heat is coming off her back and her body than it is for her hair. So her hair is a cooler temperature than her back is, right? Infrared waves are also used in heat lamps. Another additional use for infrared waves are on TV remotes or clickers. So here's my remote here, that little red dot or slide or lens in the front, that's often used as, to emit an infrared wave that your TV can read and help you to change the channel. Right? Now, these infrared waves are higher in energy than microwaves, but they're lower in energy than visible light. Right, so here's our plotting of some different properties of electromagnetic waves. So you can see some electromagnetic waves are really high in frequency. So for example, gamma rays have a really high frequency, and some electromagnetic waves, so for example, radio waves, have a really low frequency. Some waves have a really high wavelength, and some waves, like gamma rays, have a really low wavelength. Some waves have a really high amount of energy that they emit. Some waves have a really low amount of energy that they emit. And same thing with, we can see the same trend here with our energy in electron volts. So for example, that's volts is like the energy that you would have in a battery. We can see here like radio waves have a really low amount of energy in volts. And we can see some like gamma rays have a really high energy in terms of volts. The trend that we're looking at here is we want to see that as our frequency is lower, our wavelength is higher. And as our wavelength is lower, our frequency is higher. All right, so let's look at visible light. So visible light is the portion of the electromagnetic spectrum that human eyes can detect. If you remember from elementary school, Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, those are all the colors of the visible light spectrum that we can see. Red's the lowest frequency, and violet is the highest frequency color. So here's my electromagnetic spectrum again. You can see we have gamma rays, X-rays, infrared rays, radio rays. So this is the whole spectrum. The only part that we can see on this entire spectrum of light is this teeniest sliver right here. That's my visible light. So we can only see light that's between about 380 nanometers and 740 nanometers. 740 nanometers. So we can only see light in this really, really small range of wavelength. So most of the electromagnetic waves that exist, we can't see. Right, so why do we see colors? So let's take an example of the apple here. So the skin of the apple contains a pigment that reflects red light but absorbs all other colors of the spectrum shining on it. So for example here, my white light coming in, if you remember, white light is made up of all the other parts of light. So red, orange, yellow, blue, green, indigo, violet. When they combine all those different types of visible light, we have white light. So that white light comes in, it hits the apple. The red pigment in the apple absorbs all the other colors of light, but it reflects off the red light, which is why we see the apple as red. And the same thing works over here for when we have a blue object. All the other colors get absorbed, but the blue light gets reflected. When we have a white object, the white light comes in, but immediately all bounces off, so we see the object as the white light. When we have a black object, a black object will absorb the most amount of visible light. It absorbs all the colors of the rainbow, which causes the object to appear black in color. Right, now let's look at ultraviolet rays. So ultraviolet rays can cause skin cancer and blindness in humans. In small amounts, they can help your ultraviolet rays can help your skin to produce vitamin D. You might have heard that before. Go outside, get your vitamin D. So ultraviolet rays can sometimes help to promote the production of vitamin D. Ultraviolet rays are also used in tanning beds in order to get your quick fake tan that's super bad for you. And ultraviolet rays sometimes get used in sterilizing equipment. They can be used to kill some microorganisms too. For example, those that exist on maybe like if you have a case of dirty work glasses in a workshop. I've often seen those used in like a lab setting to sanitize certain types of lab equipment, right? So all our sun emits light of all different wavelengths and all different types of electromagnetic spectrum, but the one that we're most familiar with are these ultraviolet rays. And although our ozone layer of our Earth, part of the atmosphere, blocks some of the ultraviolet rays, it's important to apply skin block. It's important to wear sunblock and wear sunglasses in order to prevent sunburn, which could cause later on skin cancer and blindness from damage to your eyes. Right, next let's look at X-rays. So X-rays you're probably familiar with. They're often used in medicine, and they're also sometimes used in astronomy. They can be used to take pictures of the inside of solid objects. But if they're used too often, they can cause skin cancer. So for example, here I have a picture of a hand here. Now the X-rays can penetrate my flesh because it's less dense, but the bone, which is more dense, will reflect some of those X-rays, and it can cause us to be able to see the denser bone inside of the hand. Next, let's look at gamma rays. So gamma rays are the highest in energy and frequency on our electromagnetic spectrum, and they're often used in radiation therapy to kill cancer cells without harming nearby healthy cells. They're often used as industrial inspection tools, and they can help take pictures of the brain. So, for example, I have my brain over here that gamma rays are being used in order to create a image of. Now, it's important when we look at our electromagnetic spectrum that we see the trend between wavelength and frequency. So, for example, power lines have a really, really long wavelength, but they have a low frequency. To contrast, gamma rays have a really, really high frequency, but a really low wavelength. This is what makes gamma rays, X-rays, really dangerous. They have a really high frequency, which can really damage your cells, but their wavelength is really low. So if you're far enough away from the gamma rays, that's why when your dentist or your doctor takes a picture of you with the X-ray machine, they can step out of the room and then be fine because the X-ray or the gamma ray doesn't have a really long wavelength, but it does have a really high frequency. So remember, our trend is the higher our frequency, the lower our wavelength, and the longer our wavelength, the lower our frequency. So high frequency, low wavelength, low frequency, high wavelength. Right, so here's our electromagnetic spectrum. All combined, we can see I have my frequency plotted up here. So as frequency increases, wavelength decreases. Right, last part here, let's talk about waves and speed. So every type of electromagnetic radiation travels at the speed of light. How fast is the speed of light? 299,792 kilometers per second, or about 670,000 miles an hour. That's super, super fast. However, not all types of waves travel at the speed of light. Only light waves travel at the speed of light. So for example, sound waves are not nearly as fast as light, although they are very fast. Sound waves travel at about 760 miles per hour in air. So fast, but not even close to as fast as the speed of light. So the difference in speed between light waves and sound waves is the reason that you see the lightning before you hear the thunder. Right, and this gives us this is going to wrap up electromagnetic waves for us. And I just want to leave you with this quote from the great Muhammad Ali. So in a press conference before one of his fights, he once said, "I'm so fast that last night I turned off the light switch in my hotel room and I was in bed before the room was dark." So definitely a great quote from Muhammad Ali there. Faster than the speed of light. He might